Let's start, Oscar.
Thank you. So the title is not mine, but by Maurizio. So I beg your pardon in advance for that. Okay, so I understand that this is a quite informal kinds of talks, and so if you want to stop me for if you have any questions, please ask me without problems. And okay, so when I started to prepare this talk a couple of days ago, I decided to start from this question. I don't know if I was able to answer that, but maybe some hints about the possible answer will be given in the next. Okay, so the one very frequently asked question is how much the astrophysical bounds are accurate, are reliable, let's say. And another question is, this is a little bit more specific, the first one, no? So with astrophysics, we may actually understand if actions or other deviation from the standard physics is actually there, or we can only put constraints, bounds. And the last one is what is the state of the art for these bounds, that is where we are now, okay, and where we can go in the future. Okay, so action in astrophysics. Basically, there is an immediate goal that is the one to better understand the physics, the fundamental physics, exploiting the stars as a laboratory. That's the idea. Stars are also other astronomical objects. But for the futures, similarly to what is commonly believed for neutrinos, we may use these new particles, beyond the standard models as possible messenger. But for the moment, we have to understand if they are there, obviously. So a possible astronomical source of action, obviously stars, practically any stars may produce actions, or Alps more in general. I will talk about action, but actually I'm from the point of view of the astrophysical source, there is no much difference in between action or QCD action or action-like particles. So stars are a true thermal process, good possible producer of action. Then compound remnant, and in particular white dwarfs and neutron stars may be also interesting to explore. Then supernovae, and I have added also active galactic nuclei, so big black holes that accrete matter and stars from the host galaxy that may present some deviations from what we expect. When we model the spectra of this object, we may find some deviation from what it is expected on the base of standard physics that may bring signatures of the presence of something beyond. So the tools are the models of the astronomical source, and then the astronomical measurements, the observations. Okay. So just bounds or real detection. So here I have distinguished, but this is quite common, between direct observations, so like the one expected with helioscope, action telescope like CAST, but also in the future, baby YAXO or YAXO and so on. In that case, we are directly searching for a signature of actions, and usually this kind of as you know, this kind of telescope use the possibility to convert action into photons. And this is the great advantage with respect, for example, neutrinos. If you want to observe neutrino, you need a neutrino telescope. So weak interactions detectors, weak interactive detectors. While in case of action, you may use electromagnetic interaction because you actually, at the end, you observe the photons that are produced by the conversion, the two photons coupling there. And then there are most of the work done so far actually are indirect indication about actions. And in that case, the possibility to say, okay, I have really seen action. This is less straightforward because, first of all, because we may have alternative explanation for a deviation of some observable, no? And so we cannot be sure that actually we are observing action, an effect due to the presence of action. But by the way, this kind of indirect study are very useful to fix bounds, and bounds are important because are very useful for people that propose new direct experiments to restrict the area in the parameter space. Okay, so science case, the sun has been used to fix bounds, but very weak bounds actually, because the sun is a main sequence stars and the temperature is not very high. But being the closest star that we have, so it is an excellent target for action telescopes. Globular cluster stars has been widely used in the last 30 years, I would say, to understand new physics in general, and in particular action physics. And these provide us quite good, quite stringent bounds. So compact remnant, white dwarf and neutron stars, also in this case, we may get bounds. We will have a talk on neutron stars, so I don't say much about that. Supernova progenitor also, I will show something about that. Maybe used to constrain action physics. And there is also the possibility for the nearby red supergiant, which are supposed to be star in advanced phase of evolution and more close to the final core collapse. This may be used to detect the X-ray, an X-ray SX produced by the conversion of the action which are emitted by the stars into the magnetic fields, the galactic magnetic fields, no? And we have tried with Maurizio, Alessandro, and recently Pierluca, also Carenza, and people from Boston, from MIT, Mengiao Xiao. We have tried to use Betelgeuse, which is the nearest red supergiants, to see if to see with the neutron star if there is any excess in the X-ray flux from these stars. And so we have put limits, quite stringent limits for the coupling with photons and electrons in this way. But I will show you something later. So, and of course, other sources are active galactic nuclei, and of course, dark matter, but I think next week there will be talks about dark matter, so I will say nothing about that. Okay, so how to use STAR as a laboratory to probe new physics? A general strategy, first of all, we have to identify a stellar property, a macroscopic property, much sensitive to the new physics ingredient. No, I suppose that there are some thermal process that may produce actions, and how this process modify, for example, the luminosity of the star, or the evolutionary time scale, and so on. And then once I have done this, I should have, I can compare that with the observation, and if I find a discrepancy, a difference with respect has been predicted with standard physics, I may suspect that there is something non-standard in the theoretical models that should be considered. So that to be competitive with the laboratory experiment, the error budget should be reduced as much as possible. And the error budget, when I talk of error budget, not only the error budget of the observation, which are of course important, but also the error budget of the theoretical ingredient that I'm putting there. There are parameters which are fixed on the base of the phenomenology that should be fixed and produce uncertainty in the theoretical predictions that should be carefully considered, and this may be a major issue. So the main risk is to underestimate the global error. And if you do that, you may get a beautiful and very stringent constraint bound to the strength of the interaction with standard model particle, but at the end, this is the results of an underestimation of the global error. If you consider all the source of error, at the end, the bounds is less stringent than that. So this is something that should be carefully taken into account when we want to address this kind of study. Okay, just a very simple example of this machinery. Here you have the energy conservation equation. Now, this is one of the equations that should be solved to get stellar models, essentially. In the left hand side, we have the luminosity, the luminosity gradient, essentially, which is due to the escaping radiations. And in the right side, we have all the source and local source and sink of energy. In the standard models, these are nuclear, the nuclear power, nuclear reactions, the gravity, essentially this is the variation with time of the entropy, that may be due to a variation of the internal energy, or a variation of the volume, so a compression or an expansion, or a variation of the chemical composition. And finally, there are thermal neutrinos. These are not the neutrinos produced by the nuclear reaction, which is included in the first term. So we subtract the energy from the energy produced by the nuclear reaction, but these are thermal energy, thermal process that may produce neutrinos. And of course, this is the conservation equation. So if you integrate that over the full structure, you get the luminosity that is what we observed. And so you may compare the luminosity predicted and by the model and the luminosity observed of the star. And suppose that you find a discrepancy. How we can interpret the discrepancy? Well, one possibility is that there are uncertainty in the theoretical recipe and in the observations that may explain this discrepancy, or there is missing physics. There is some missing physics, and that's what we want to investigate. Some example of missing physics concerning the equation we have seen before. A non-vanishing neutrino magnetic moment that will enhance the neutrino rates, energy loss by neutrinos, a non-standard energy sinks something beyond the standard models. For instance, a production of axion or axion-like particles. So in additional terms, this the last one, the red one. Or additional energy transport mechanism. This is another question that I have not shown before, but I will show then later. Suppose that you have a particle that may be particles that may be produced by thermal process, and then they move with a certain mean free paths, and then it decay or interact, and it is absorbed, so release energy. All these inside the stars. No, when we talk about neutrino or massless action or action with more mass, the mean free path is so large, so long, larger than the stellar radius. So this is actually considered as an energy sink, no? But in case of this more massive particle that can decay within the star, in this case, they contribute to the energy transfer from the hot internal part toward the exterior, no? So in addition to the radiation, the convection, conduction, and so on. So all these modify the stellar structures and produce a modification of the observables, and we hope to detect that in some way. So some example of theoretical errors concerning the standard physics, no? In general, any uncertainty that affect the determination of the rate of energy production and sink, no? For example, unknown low energy nuclear states may affect the fusion cross section and in turn our evaluation of the nuclear energy production rates. Some example of observational error, this is straightforward. So systematic error affecting the photometry, the distances, the light extinction along the line of sight. Now we measure a luminosity, but if the light traveling from the astronomical source to us has been absorbed by the gas, the hydrogen column that is in the middle, this should be carefully considered, but because produce and may produce uncertainty if you are not able to model that with accuracy. Okay. So so the condition to be able to say without any doubts, I mean, I'm really seeing action. No, be sure to have considered all the error once again, all the uncertainty, both in theory and in the observations. And there are no alternative explanation. And this is suppose that you have been able to take into account all the uncertainty and you have made your best to reduce them, no? And still you find a discrepancy. So the discrepancy is still there between theory and observations, standard theory and observation. So you say, okay, I have seen action. No, because there may be some alternative explanation to explain this modification of the macroscopic property that I'm observing. So in this sense, this kind of study, indirect study, are very good to fix bounds, but not very upper bounds, but not very good to fix lower bounds or to say, definitely I have seen actions. So globular cluster star. Let me say something more about that. The globular clusters are building blocks of any galaxy. We found globular cluster, of course, in spiral galaxy like the Milky Way, but also in elliptical galaxy. And practically in any kind of galaxy, also in the small satellite, dwarf spheroidals, or irregular galaxy, the small satellites of the system Milky Way, M31, Andromeda, we see globular cluster, different because the star formation process is different in different kind of galaxies, but in any case, they shared the same characteristic, that being a group of stars of typically of the order of 1 million stars bounded gravitationally, so by the self-gravitation. And this is the reason for which they appear globular, no? It's a sphere, more or less. Okay, so globular cluster stars are excellent laboratory to investigate new physics because we have a large number of stars, so a good statistic in general, and almost homogeneous stellar sample, even if this is an important point, because recently it has been understood that actually globular cluster contain multiple stellar populations. So originally it was think that all the stars of the globular cluster formed of the galactic globular cluster in the halo of our galaxy formed in a very short time from an homogeneous chemical composition, same composition, same helium, same abundance of metals, and so on. So they are a very homogeneous sample of 1 million stars, and that is very good. Actually, it was discovered recently, both spectroscopically, both photometrically. There are many evidence that practically all the globular clusters, the galactic globular cluster, host more than one population, and there are various interpretations. I should say, oh wow, from where these multiple population, stellar population comes from. Even if I would say that till now there is not a satisfactory explanation for that. But anyway, they are there, and in some cases we have large differences in the chemical composition, in the initial chemical composition, for instance, the helium abundance, and this should be carefully taken into account when we address our study on axions. Okay, so this is the color magnitude diagram. So here we have the magnitude, which is essentially the luminosity in a portion of the electromagnetic field, and here we have the column. The theoretical counterpart of the color is the effective temperature, the temperature at the base of the photospheres of the stars, or if you want, the temperature of an equivalent black body. No, you have the spectra, and what is the black body that may reproduce this spectra? Okay, which is the temperature, and the temperature, and this is the effective temperature. Okay, so we have different, we recognize different sequences, no? The most important is the main sequence. The most populated is the main sequence, which we know from models that correspond to hydrogen burning stars. Then the star evolve at the turn-off point, the TO, hydrogen is exhausted, and the star, there is a transient between the main sequence and the red giant, this RGB, red giant branch that you see there. So the external layer of the star expand, the core start to contract to release gravitational energy, and doing that, about half of the energy goes into thermal energy. So the core heat ups, and the other half is extracted, is emitted by radiations, and then the stars start to climb along the RGB that is made of this contracting helium-rich core with an hydrogen burning shell just outside the core, and then an extended convective envelope outside, and they appear as giant, no? Several tens of the solar radii, and this expansion of the envelope and contraction on the core continue until in the center, not in the center, but in the core, let's say, actually off center because there is neutrino cooling in the center. The temperature reach almost 100 millions of Kelvin degree, which is the temperature at which the triple alpha reaction start to burn helium into carbon. And so this is and since highly degeneracy of the electron component is developed during the contraction of the quartz, and the peculiar equation of states of degenerate matter produce a thermonuclear runaway that is called the helium flash. So immediately the star leave, when this happens, leave the RGB at the tip of the RGB, this happen, and move in the horizontal branch, the HB, which is the quiescent helium burning phase. At the end of the helium burning, during the helium burning, you have this nuclear power, the helium burning in the center. Helium is burned into carbon by the 3-alpha process, and then carbon may capture an alpha and produce oxygen. So this is very important for life, because this is the main source of carbon and oxygen, which are two important elements for the survival of all the known life species. And so then at the end, you have when helium is exhausted in the core, the star comes back to the giant branch and becoming an AGB, an asymptotic giant branch star. Asymptotic giant branch star, usually there is a first part that is called an early AGB, in which we have two burning shells. No? The product of the helium burning is a core of carbon and oxygen that restart to contract again. And outside we have an helium burning shell, an helium mantle. At the base we have an active helium burning shell. Outside we have the residual hydrogen-rich envelope, and at the base of the hydrogen-rich envelope there is the hydrogen burning shells. So we have two active burning shell, but then since the helium burning is much faster because it's less efficient, so burn more rapidly than the hydrogen burning, when the helium burning shell get closer to the hydrogen burning shell, stops. And this is the beginning of the thermally pulsing phase. No, the thermally pulsing phase, for most of the time, the luminosity of the star is provided by the hydrogen burning in the shell. But when a certain amount of helium is accumulated below, there is an helium ignition that produces a thermal runaway once they wane. So we have a series of these cycles, which are called the thermal pulses. And this is the asymptotic giant branch stars. Okay, so remembering this evolutionary phase, these are observable, possible observable, that may be exploited to investigate this process, this thermal process that may produce actions inside stars. So I will talk about the luminosity of the RGB and of the air parameter in particular today. Okay, but there are also others that may be exploited and could be investigated. Okay, so data requirement, we have to collect a good statistic, and this implies to combine observation from Earth with large telescope. But the problem when we observe from the Earth is that the atmosphere is turbulent, and so a point line source actually is spread on the photometric plate, and so this prevents the possibility to separate, to resolve star very close. And when we go in the core of a globular cluster, where most of the stars are concentrated, in particularly the most massive one, so which are the evolved one, that segregate over the center. They are old objects, 13 gigayears, 12 gigayears. So they have time to segregate under the mutual interaction, gravitational interactions. And thanks to space telescope, it is possible to resolve the cores and to search and increase the statistic. So we combine big observation from the Earth to obtain the neighborhood, the images of the neighborhood of the cluster, and the core is resolved with space telescope. You know that last year has been launched the JWST, that is the new space telescope, and hopefully JWST will produce much more resolved stellar population, not only in our galaxy, but also in nearby galaxy. Okay, so this is done. Then we need astrometry, and we have this to derive distance and to distinguish between stars that actually belong to the clusters and contamination by field stars. We have to eliminate these contaminations. It is very important. We can do that by measuring the so-called proper motion. No? This is some kind of precise measurement. Okay, coming back to the theory, this is the rates of the various thermal processes that may produce action. These, of course, are mainly based on the long-standing work by Georg Raffelt. And I will say nothing about that. The only things that I should note is that essentially the larger is the temperature, the more efficient will be the production. And some of these processes, most of these processes, except Bremsstrahlung, are suppressed in case of electron degeneracy. So in red giant star, in the core of red giant star or asymptotic giant star, or on white dwarfs, only Bremsstrahlung can be a possible source of actions, while in other evolutionary phase, additional processes like the Primakov or the Compton or the E+, minus massive stars, the annihilations of electrons and positons may provide the source of actions. Okay, these are considered very simple stellar models, the simple in which you like the sun actually, you know? So as slow rotators with negligible magnetic fields. In that case, you may assume spherical symmetry, and the equation that describe the stellar structure are this one. So we have the hydrostatic equilibriums, the mass conservation, the energy conservation, and the energy transport equations. And finally, the last equation is describing the evolution of the various chemical species by nuclear reactions or by mixing, for instance, those induced by convective mixing. So you need appropriate boundary conditions in order to solve that. And typically, one stellar models, so one time step, contain something of the order of 1,000 mesh points. So 1,000 value of the mass from the center to the surface, to the total mass M. And an evolutionary tracks that is describe the evolution from the pre-main sequence up to the final end of the stars imply a calculation of something like 20,000 stellar models. This is to evolve a low mass star from time 0 to 13 gigahertz, let's say. Okay, this just to give you an idea. So the first observable that may be employed that I want to discuss is the air parameter, which is the ratio between the number of stars observed in the horizontal branch and the number of stars observed in the brightest part, brightest than the so-called zero-age horizontal branch in the red giant branch. While this number is interesting because this essentially measure a ratio between the time scale of the evolution of the hydrogen, of the helium burning, and the time scale of approaching the helium flash of RGB stars. And the time scale, and this is because, of course, the faster is an evolutionary phase, and the lesser is the number of stars that I have observed in this evolutionary phase, or the larger is the time scale, the larger will be the number of stars that I have observed in a given evolutionary phase. So this ratio has been largely used in the past to probe the stellar models. And what is interesting that it is independent on the metallicity. So I can repeat that with several globular clusters and to combine the information, because essentially the only thing that the worst thing is that it depends on the amount of helium. So if you have difference in the helium content from cluster to cluster or from star to star of the same cluster, this may be a problem, as we will see. Okay, so this is from a catalog of a globular cluster, the calculation of the air parameter, 39 globular clusters, and this is the weighted average, this error that one can get. And so this is our observable that we want to compare with the predictions. Okay, so theoretical prediction, we start from evolutionary tracks. So here you see one evolutionary tracks of the RGB, but then you have 10 HB, horizontal branch, helium burning evolutionary tracks. Why 10 for just one? And this is because during the RGB, there is mass loss. And this mass loss is a sort of stochastic process. So different stars may undergo different mass loss during the RGB. And so the mass that is left at the flash, at the helium ignition, may be different from star to star. And this is evident because this mass variation, total mass variation, produces a spread in the color, or in the effective temperature of the HB stars. While this mass loss have a negligible effect on the red giant. But when I go into the horizontal branch, I should take into account that. Okay, so this may complicate the calculation because, of course, I have to calculate much more models, stellar models. But by the way, this can be done. Okay, so an help in comparing what we observe with what we predict theoretically is obtained by means of this synthetic color magnitude diagram. Essentially, what we do is that we have three parameters, which is the initial mass that is distributed according to a mass function, a so-called Salpeter mass function that's come from the star formation process. So the HB mass spectrums that is Gaussian in these simulations, and here you see the 1 sigma of the Gauss function. And then we have to take into account the photometric error. So on the magnitude and on the color. And this is what we predict by assuming two different central value for the mass on the HB. And you see how the HB change significantly playing with these parameters. So this is something that should be adjusted cluster to cluster in some way. By the way, I can, once I have done that, I can repeat exactly what I have done on the observations and count how many horizontal branch stars are predicted and how many RGB stars are predicted and get the air parameters. So multiple populations. So the problem here is that this lifetime depends of the HB depends on how much helium. No, sorry. Actually, both the HB number and also the RGB number depends how much helium there is at the beginning in the gas from which this star formed. So suppose that here in this simulation I have assumed two different populations, stellar population, one in blue, an original one in black, and in red is a second populations which helium enhanced. And you see if that the difference in the helium abundance, this is the mass fraction. Y is the mass fraction of helium. So 24.8% means that this number in mass. And you see the effect where the different stars of the different populations are found. And the reason for which the helium-enhanced stars are bluer, no, are hotter, is because it's very simple. That actually, if you have if you start with a large amount of helium, you have less hydrogen actually, and so the main sequence time scale, which dominates in determining the total lifetime of stars, is much faster. So this means that if the cluster age is 13 gigayears, on the average, the population with low helium is massive, is more massive than the population with a large helium. So the large helium star have a mass smaller on the average. And this is because the stars are like, yes, 20, 10. Okay, more or less. So stars are like the cars, no? You have a Ferrari, they go very fast, but they consume the fuel very rapidly at a fast rate. And then you have the 500, Fiat 500, not the new one, but the old one, or the 50, that go very slowly, but they consume, or at least should consume the fuel at a slower rate. Now, you understand the joke, okay? So this is to say that with the same amount of initial fuel, hydrogen in case of stars, the 500 can do a longer path with respect to the Ferrari. And the same are the stars. So the small mass, so the relation between the luminosity, which is the rate at which energy is lost, and the star evolve because they lose energy, the relation between luminosity and the mass, which is the fuel, okay, is not linear. Now the luminosity is proportional to at least to the cube of the mass, something between the cube and to 4. Okay, and so this make this is the reason for which in globular cluster we observe low mass stars, because the more massive are already evolved and disappeared, and because they go fast like the Ferrari. So this is the results of this simulation, and you see that when the difference in the helium content of the two populations becomes enough large, the air parameter is affected. So with a single population, we have this number, and you see that, unfortunately, most of the globular cluster in our galaxy show little variation of the helium between the different populations. But there are a few in which, for instance, Omega Centauri is one, the biggest one typically, in which the difference between one population and the other population may be even larger than this one. And these affect the air parameter. So you have to, or you are able to distinguish between the different populations, or you have to discard this cluster. This cluster cannot be used. And this is what we do, looking at the HB. The ones that have this long tail, blue tails, are excluded in our sample. Okay, that's the way in which we treat. This is illustrated the kind of result we expect. So these are models, the air parameters versus the helium abundance for different assumptions about the coupling with photons. And you see the observed air parameters where it is with the uncertainty we estimate for the initial helium and the measured air parameters. And you see that there is a little discrepancy between what we observe and the standard models, that is G10 equal 0. So this is a little hint in favor of an additional cooling. Okay. So here in this plot here, I have just considered the coupling with photons. So the coupling with electrons, so no Breslalong in particular, no Compton has been taken into account, only Primakov. that affect the HB lifetime, because Primakov is suppressed during the RGB. And the variation of the RGB time scale is very small due to the residual Bremsstrahlung. Sorry, the residual Primakov. Okay, so this is the kind of results that we get. Of course, you have to consider all the sorts of uncertainty. There are many, especially on the HB, the horizontal branch, something related with convection, turbulent convection, nuclear cross sections, of course, that are the nuclear power. So the uncertainty in the recipe, the theoretical recipe that I'm using. And here you see the Monte Carlo used to combine and to search for an eventual correlation between these uncertainties. And this is the kind of result that we get. I have other. This concern in particular the variations when we consider in the first case the variation of air induced by a variation within the uncertainty of the cross section of in this case the reaction rates of the important carbon-12 plus alpha reaction. This is considered the holy grail of nuclear astrophysics. The reaction is the subject, the target of an enormous amount of studies in the last 50 years, and still we have to extrapolate to lower energy the rates, the cross section, sorry. And the problem here is that there are subthreshold resonances that may interfere with high energy resonances, so nuclear state. And if these interference are constructed, the rate, the cross section is enhanced. In case of destructive interference, instead we have a suppression. This is the state of the art in a recent analysis, air matrix analysis. And air matrix is phenomenological models of these nuclei. And this is what is obtained. And considering this uncertainty in a Monte Carlo, we get this kind of results. And also for other important reactions like the triple alpha and the nitrogen 14 P gamma, which is the bottleneck of the hydrogen burning, of the CNO burning in shell, and so on. So this is the kind of result that we get. So there is some hint around 0.29, 10 to minus 10, for the coupling of action with photons, and an upper bound 95% confidence limit at 0.65. This was also the results obtained in a paper in 2014, Ayala et al. And then was also similar to the bounds obtained by Cass later, a couple of years later, in 2017, 2016, by the Cass collaborations. So at present, this is probably the most stringent bound for G alpha gamma, GA gamma. Okay. So of course, one may switch on the electron coupling. No, of course. In that case, you have one more parameter to consider, and this is so you have to vary the GA gamma, GAE, and of course the helium, which is the third ghost in these games. And this is the kind of likelihood in 2 dimensions that we get, and the result is this one once again. So basically, of course, if you have, and this is true for massless, let's say, action. So for action with small mass. But if you increase the mass, you have to consider also other processes like the photon coalescence and the possibility that alpha may decay within the star. And so And so they contribute to the energy transfer rather than to be an energy sink or only an energy sink. And this was studied in this paper, these two papers by Pierluca Carenza et al. In 2018 and Giuseppe Lucente in 2022, very recently. And this is the kind of bounds we obtained from the HB, considering this possibility that the energy transfer in stars is modified by massive actions. Okay, so that's the conclusion of these stories. Another, I have time to say something? No? Zero. Are you sleeping? No. Can I continue at the 5 minutes? I don't
5
know.
minutes. 5 minutes.
5 minutes, it's
Yeah,
okay.
5 minutes.
Okay. So. Okay, this is another interesting observable. That is the luminosity of the tip of the red giants, no? The red giant stars. Okay, so essentially, the Bremsstrahlung action, which is not totally suppressed in case of degenerate electrons, makes the illumination occurring at higher luminosity, so brighter. And so we may exploit that to constrain action physics or decoupling with electron, let's say. So this is an helium flash when the star ignite. This is the first flash, 10 to 10 solar luminosity is attained, and then various flash. And the flash occur off center because in the center we have a cooling induced by neutrinos at high density, plasma neutrinos, plasma decay. And so actually the temperature is maximum around 0.2 solar masses from the center. And here, firstly, ignite helium, this flash here. And then the temperature, the heat is transported toward the center. The energy released by this flash is moved toward the center. So you have more flash going toward the center, less the stature, the correspond a bit. So the degeneracy, the degree of degeneracy is lower and lower until the star settles on the horizontal branch, the HP, there, from the flash, making big loop, not shown typically, until it's settling in a very short time, less than 1 million here. So this is a short time in astronomy. Okay, so why? And this is in a red giant branch star. I don't remember the luminosity, but it should be close to the helium ignition. So a comparison between the neutrinos energy loss rate and the action energy loss rate. Also in this case are low mass actions. Okay, and you see that while neutrinos are sensitive to the density, essentially plasma neutrinos, the maximum of the action production is where the maximum of temperature is. Okay, so in any case, this is lost. Both are lost and contribute to determine the moment in which the luminosity at which the helium burning start, the flash start. Okay, so this is the effect on the bolometric magnitude, so the luminosity at the tip as a function of the coupling with electron, of action with electron, okay? So this is a standard one, and so increasing the coupling, the strength of the coupling, we have a major effect on the variation of the tip luminosity. Okay, so the magnitude goes at reverse. So smaller magnitude means brighter stars. Yeah, that's okay. So this is what we do. Once the gains, error are important. So this is the various input physics in the models, the standard input physics into the models. So the mass loss, the nuclear reactions rates, the nitrogen 14p gamma, the triple alpha, the screening electrons are polarized in a plasma at high density. And so this reduces the Coulomb barrier seen. No? When you measure the cross-section in laboratory, you have bare nuclei, okay, in most cases. Or if you have screening, you have to cut the effect of the screening. But then in the plasma, you have screening induced by the electrons. And these reduce the Coulomb barrier and then enhance the cross-section. So it is very important how to calculate, and the coupling is weak, you may use a sort of the Euclid theory, which is the first order solution of the Poisson equations for the electrostatic potential. But in case of strong coupling, the situation may be more complicated. So people talk about intermediate screening and strong screening in case of intermediate coupling or strong coupling, rather than weak coupling that is good for the sun. In the sun, the weak coupling approximation that the bi-Euclid work quite well, but not in red giant stars. So then we have the conductivity. The generate electron produce energy transport, a very efficient energy transport, because you have the Fermi, the electrons are piled 2 by 2 in the energy states in the Fermi pile. And then they, when they interact with other particles, or they do not find free space in the parameter space. And so only the most energetic, the ones with the energy close to the Fermi energy, can interact. And so this is to say that the mean free paths of the generated electron is much longer than the mean free paths of non-degenerate electron. And so for this reason, they they contribute to the energy transport in the core of a giant stars, and this is very important. Of course, the radiative opacity is also important for the more external layer. The mixing length is something related with the convection in the envelope. So the boundary conditions at the external, at the surface of the stars, the equation of states, microscopic diffusions, so the gravitational settling, for instance, that occur during the main sequence that change the chemical stratifications. In case of rotation, we may also have an effect due to the centrifugal force. So you have to evaluate all this uncertainty according to what we know about this input physics. And this is the kind of effect we have on the magnitude of the bolometric magnitude of the tip. Okay, so in principle, you may have a correlation between them. And so this is the machinery that we have. We start from a selection of a set according of the parameter of the input parameters according to the distribution function that we assume for each one. And then with this, we calculate models up to the RGB tip and determine the luminosity that is stored. And then we iterate that for several times, thousands of times. And then at the end, we get this distribution of the global error, the global uncertainty with respect to the central value. And so this is the global theoretical uncertainty that we get, 1 sigma, let's say, in this way. So then there are a global cluster catalog log, the parallax from Gaia data release tree, that is important for the distance, then proper motion from Gaia, from HST, to understand distances and membership, multi-band photometry to get the bolometric magnitude to be compared with the predictions of the models, and so on. And let me skip this one. These are details. This is also important, but I have no time to discuss that. And just to say that distance is still a major problem, and great advancement has been recently obtained by combining different methods, independent methods, to get the distance of globular clusters. And this is the results that we get. So the black line, solid line, is the result obtained with no actions. And the red dotted line is the last square feet of the observation, the red dot. And this is the case of, this is an error. This is not G10, but it's G13. This is the coupling with the electron. So this is wrong. I should correct that. And this is the kinds of likelihood that we get. And this is the results, the latest results. And just to show you, since this method started many years ago with a paper on M5, or the cluster M5 by Vio et al. In 2013. And then there are several other exploitment of this method of the RGB tip until the last one. And here you have the reference if you want to have a look to that. So, and this is, just let me finish with this one. This is a slide I stole to Maurizio Giannotti, in which there are several past and future experiments, telescope, like Baby Jackson, and Yaxo Plus, then Darwin. And so how this parameter space is constrained by the constraint on the air parameters, by combining the constraint on the air parameters and the constraint from the RGB tip luminosity, so we can exclude the yellow area. So this could give you an idea of how important this bound, no? Because it's telling to the people that are proposing new experiment where should be searched. What is the sensitivity that should be reached? Okay. So this is the end of the moment. Oh, this is another story. I don't want to begin with that. Okay, thank you. Sorry for being too long. Incomplete. Sorry, but could you? Unknown? Nuclear?
An unknown nuclear state.
Ah, yes. Yeah, you know, so if you exclude very simple nuclei, like hydrogen, of course, or deuterium, which is the simplest one, most of the nuclei that interact and produce energy in stars are many-body objects, and so a clear an ab initio model, let's say, of this interaction it actually don't exist. So what people do, we have phenomenological models like the R matrix that I have shown in the case of the carbon 12 plus alpha. But this depends on the information from an experiment. For instance, the energy of a resonance state or the gamma. And all these information are not predicted by the theory and should be derived from measurements. And when you go to low energy, you face the problems that you have contamination from cosmic background or natural background. And so the signal to noise ratio becomes so prohibitive, so small that you cannot go at low energy. And in star, you actually have low energy. So so you have to extrapolate for high energy measurements. And if you are missing something at low energy, these imply that you are underestimating or overestimating the cross section and then the reaction rates. The example of the carbon-12 plus alpha is typical. In that case, the measurements arrive up to 1 MeV, but the gamma of energy, which are the energies at which you have the largest probability to have the reaction at the typical temperature of the helium burning, is around 300 keV. And so you have to extrapolate from 1 MeV toward the cross section toward the 300.3 MeV. And the problem is that in this region, this hidden region, you don't know if the resonances, high energy resonances, and subthreshold resonances interfere, and so you may only try to constrain that. You don't have a theoretical indication of that. The theory tells us that the interference may be constructive or destructive, but you don't know exactly how it is. And this may produce even a factor of 2 uncertainties in the reaction rate, which is a lot. Now we are improved measurements that have constrained more this uncertainty, and now the presence uncertainty is of the order of 30%, which is very good in many cases, but not definitely good. The idea is to have new experiment in the future that can go at lower energy and constrain this cross section at the level of 10%. This is the ideal. But right now, still.
What could kind of mention, right? But experimentally, to go to very low energy, you need essentially
the stand.
Underground.
If you go underground, you suppress the cosmic background, no? But not the natural background, for instance, or the beam-induced background. So it's a complex stuff. And dependence on the reactions. For example, for the nitrogen 14P gamma, we get to reach with Luna, no? The laboratory for underground nuclear astrophysics is in the Gran Sasso laboratory. We get the energy gamma, the gamma of peak energies for this reaction in the shell hydrogen burning in RGB stars. So we have an experimental error, a direct experimental error. That's very good for the cross section of these reactions by suppressing the background. But this depends on the gamma that produced, no? Because you measure the gamma produced by the reactions. So this depends on the energy of the gamma, where in the spectrum of the natural background or the beam background or the cosmic background felt. So then there are tricks to reduce also, for instance, in the new accelerators, the Luna megavolts, we use a box of lead at low radiations, at low content of radioactive to screen the detector apparatus, and so to reduce also the natural background, let's say, the radon, essentially. That have a spectrum. So if your gamma is where the radon produce gamma, you can see nothing. So it depends on the reactions in general.
Quick question. I guess whoever was there is a quick question. Yeah. Also,
sorry, there is. I have difficulty to understand because there is an echo from there.
So there are compact remnants.
Yeah.
Such as white dwarfs and neutron stars.
Yeah.
In globular clusters as well.
Yeah.
So is there any special observable like this R ratios?
Oh, in globular cluster, you mean? In this kind of constrained action in general?
R ratios.
Yeah, no. In globular clusters, white dwarfs are very faint, are extremely faint because they are old. So they have time to cool down. So you find And so HST, the Hubble Space Telescope, have seen in some globular cluster the sequence of, later I can show you something if you want, the sequence of the white dwarfs along the cooling sequence, but they are very faint. And since they are faint, that means they are also cool. And since they are cool, the action productions, the neutrinos or action, the thermal production of particles is strongly reduced. The white dwarfs, that are most interesting for this kind of study are the hottest one. The ones that are in the cooling sequence, entered in the main sequence very recently. These are the ones that still are hot enough to have thermal energy to produce these particles. And so in the fields of the galaxy, there are many of them. And Gaia, I've seen many of them. So rather than globular cluster, the field white dwarfs are studied. So
there are some methods, special methods for studying axis in white dwarfs. And if you want, we can also discuss that.
yeah, basically there are two observable. One is the luminosity function, which is how much what is the number of white dwarf observed in a given luminosity intervals. And this is and this is the luminosity function. That is affected by the cooling process in the hot part of the cooling sequence. And then the second observable is the cooling time scale. And this can be observed, for example, there are some of these white dwarfs are unstable and pulsate. And the pulsational periods increase as time passes over. So the rate at which the pulsational period is reduced, the reduction rate of the pulsational period is a measure of the cooling rates. That's the idea. And this is another observable that has been successfully used also in conjunction with asteroseismology experiments of white dwarf, asteroseismology of white dwarfs to measure the cooling time scale and then the physics that determine this cooling.
Everybody, I guess maybe